So much of the middle and high school math curriculum revolves around functions as a central theme that runs all the way through from 6th grade up through 12th grade and beyond into the sort of calculus-based curriculum in college, right? In large part, we have Felix Klein to thank for this philosophy. He was one of the first early voices that sort of said, hey, we should be studying functions in middle and high school because not only are they a rich source of mathematical ideas, they're also a rich source of applications, right? That if we're going to learn how mathematics gets integrated into other modes of thinking and reasoning and other disciplines of study, functions play a central role in all of that stuff as well. And functions are in the background of a lot of the stuff that we do in the 6 to 12 curriculum, even if we don't necessarily always tell students so, right? In our last video, we talked a little bit about how the nature of the square function leads to this teaching conundrum, where we tell students that the square root of 16 is equal to 4, but then when they solve the equation x squared equals 16, there's this other solution that doesn't show up if all we do is take the square root, right? And the reason for that ambiguity is that the squaring function, if I square real numbers, the distinction between numbers that can easily get lost is the sign, right? Positive 4 and negative 4 are different inputs, but once we pass them through the squaring function, they give us the same output, 16. Right? And so there's a function property going on there, that the squaring function is able to take two different inputs and produce the same output. Right? And so we want to understand what properties of functions are salient, what properties of functions are most important for us to understand if we want to fully kind of grasp what's going on with questions like these in the middle and high school curriculum. So in this video, let's take a look at what I hope is going to be some familiar terminology for functions and how they show up typically in the sort of high school curriculum. But these are ideas that we want to take from the high school curriculum and then kick them up another notch to be able to study complex functions so that we can get a handle on what might be the same as when we studied it in the real case and what new possibilities might exist. So first of all, probably the most fundamental definition for functions in this section is the idea of a function being one-to-one. So I call a function one-to-one, or I might use the word injective if I'm feeling fancy. A one-to-one function has the property that different inputs always give me different outputs. So the thing a one-to-one function cannot do is it cannot take two different inputs and produce the same output from them. That would be a failure of the function being one-to-one. So because it's convenient for us this week in particular, if I have a function which is not one-to-one, we'll call it many-to-one. For example, the squaring function, we might call it a 2-to-1 function, because in general, the generic example is that plus and minus a positive real number will get squared and give us the same result. So it's 2-to-1 in most cases. The one counterexample to that would be 0, right? 0 squared is the same as the opposite of 0 squared. So one-to-oneness is important. Where does this show up in the high school curriculum? Well, it can show up just by analyzing properties of graphs. So one way to do that is by using a horizontal line test. So probably this shows up in the high school curriculum when you're first learning about inverting a function, finding the inverse of a function, right? And so a function is one-to-one if and only if it's not possible for me to draw a horizontal line on its graph that intersects the graph more than once. Right? So here's a function graphed in red, and I can pick some different horizontal lines. Some of these horizontal lines seem like they pass through the graph. Some of them don't. But those horizontal lines which do pass through the graph only pass through the graph in one spot. Right? So this is an example of a function whose graph sort of passes this particular horizontal line test, right? And so we would say that this function is one-to-one. It's not possible for me to draw a horizontal line that intersects this graph in more than one spot. And so a function which is not one-to-one would just break that principle at one or more places, right? So here, for example, some horizontal lines seem like they intersect this graph only once, right? This horizontal line does, this horizontal line does. But there exists at least one horizontal line, and in fact probably infinitely many in this case, right, which intersect this graph in more than one spot. And so this function would not be one-to-one. You might recognize this graph as looking something like probably the graph of a cubic function, a third power function, that is where I got this graph from. And so according to the fundamental theorem of algebra, a cubic equation could have as many as 3 real solutions. It could have fewer. Right? In the case of picking this horizontal line, we only get one solution to the cubic equation, which is equal to 4.4 in this case. But there are some places where we get 3 solutions. So this would be a not 1-to-1. It would be a generically 3-to-1 function. In some places it would be 1-to-1. In a couple places it would be 2-to-1. Right? If we intersect just right at the top of this this hill here, or the bottom of this valley, there'd be 2 places exactly where this line intersects the graph. But in general, as soon as we have even one place where there's even more than one intersection between a horizontal line and the graph, we can say that that function is not 1-to-1. So 1-to-1ness, as you might expect, is the fundamental property that we're going to need in order to even have a chance of computing an inverse for a function, in order to be able to go backwards. If there are 2 different places, if I have 2 different inputs that give me the same output for a function, and functions can do that, that's totally fine, as long as there's not more than one output for a given input, right? It would not be possible for me to go backwards and have that backwards correspondence be a function, because that backwards correspondence would have to go to 2 different places. So 1-to-1ness is a really fundamental property that we're going to insist that functions have if they're going to have a chance at having an inverse. The other function property that tends to stand alongside 1-to-1ness is called onto-ness. So a function is called onto, or if we're feeling fancy, we say surjective, if every single element of its codomain is realized as an output of the function. In other words, if we can always solve the equation y equals f of x for any y, any left-hand side in this example that I could put into that equation. So onto means that everything in the codomain is getting hit by something from the domain. Or another way to say that is that the codomain and the range of this function, the realized set of outputs, are one and the same. So graphically speaking, we can use horizontal lines again to interpret what it means for a function to be onto. So this function looks like it would be an onto function because there is no horizontal line that I can draw that doesn't intersect this graph in at least one place. Right? So an onto function, every horizontal line intersects the graph of f at least once. So every output has at least one input that produces it. Every output that I could choose, in this case, any y coordinate on the y-axis, I can realize as the output of this function for some value of x. And that makes this the graph of an onto function. Whereas this might be an example of a graph which is not the graph of an onto function, because while there are some y values I can choose which do result as the outputs of this function for some x, there are also some y values that I can pick that don't seem to result from the output of an input given with some x, right? I can draw some horizontal lines that don't seem to intersect this graph at all. And so there would be no x for which f of x is equal to these y's up here and down here. And so this would be an example of a function which is not onto. So 1-to-1ness is important because we'd like to be able to go backwards and have a unique answer when we go backwards so that we can reverse the process that the function applies and call that reverse process also a function because it has a unique output for every input. Onto-ness is important so that that reverse process can be defined everywhere on the codomain of the original function that we selected. And so when a function satisfies both of these properties, we give it the special name. Let me highlight this one in a different color. We call it either a 1-to-1 correspondence, which I think is an unfortunate choice of terminology that many mathematicians use because it sort of is confusing with the idea of a 1-to-1 function. It's not the same thing. So very often we'll use the word bijective or a bijection to describe a function which is both 1-to-1 and also onto. It's 1-to-1, so different inputs always give me different outputs, and it's onto so that every output in my codomain is hit by some input from the domain via this function. And so these are going to be the functions which we can not only reverse and have the reverse process be a function because the original was 1-to-1, but also it will give us a reverse for every single element in the codomain because the original function was onto. Those are the functions we would like to invert and have the inverse be an actual function. In the next video, I want to kind of pop the hood at how we can define inverses of functions. Even if the function is only 1-to-1 or if the function is only onto, we can still get part way toward defining an inverse function. But in order to get all the way there, we would need to have both of those be satisfied. So stay tuned for the next video where we're going to talk about what it would mean for a function to have a left inverse, what it would mean for a function to have a right inverse, and then functions which have both which we call invertible functions.